Recording. Yep, I'm recording, and we are heading over to the share screen. And let me hope that you guys can see the screen. Can you see the screen? Yes. This is always the sort of the defining point of my day. Because if you say yes at that point, I know that things will be good and that we are going to have a good session. And the attendance, thank you very much. Bernardo, quotation marks, Moodleman, has already posted the link. So thank you very much. That's absolutely great. And I think people have already started with task 1 for the BI308 for this assessed practical. I don't think it is too challenging, but if you've got problems, you know where to find me, don't you? And it is for all students. That includes the biomedical engineering students and also the students on the International Foundation Program. And what we are going to do today is, we are doing more Vmaxes, yes. You don't like Vmax, Daria? Oh, I'm terribly sorry. You see, Vmax is one of the absolutely key parameters. It's one of the key parameters of an enzyme. So I'm afraid we are going to deal with it for the next, 38 weeks. Not feeling this module yet. Don't worry. Don't worry. You will feel this module. It will come to you. I promise you. And don't despair. And I'll tell you what, I let you into a secret. Shall I? Regardless of what you're going to say. When I got appointed on a temporary lecture post, that was 25 years ago at the university here, they asked me what topics I would like to teach. Yeah, at that time, you could really sort of say what you enjoyed teaching. And I said, I would not like to teach microbiology because I'm not a microbiologist. And the other thing that I would not want to teach is enzymology. And the interview panel said, well, with the microbiology, don't worry about that. But enzymology, this is exactly what we want you to teach. And I went home, my heart sank, and I thought, well, you can imagine what I was thinking at that time. Why did I not want to teach it? Just simply because I didn't get it when I was at university. So I was totally in your boat. I had no idea what Km was, what Vmax meant, what the heck, right? Well, I thought, there's nothing I can do about it, so I need to learn it. And the more I looked into it, the more fascinated I became. And I thought, that's actually, the topic is really, really interesting. And you can do so much with it. And I started to totally fall in love with it. And I'm afraid now you are at the receiving stack of that. Do people actually, I assume for other people things are working. So Aman, I'm not entirely sure what's going on. But as people say, try again and don't do the rice thing, please. Okay, let's get started before I get totally emotional about my love to enzymology. No, don't throw it on the floor. Don't tell him things like that. It wasn't like Stockholm Syndrome. I really enjoyed it because I found a really good course that taught me that. And what I am trying to do in my teaching here on this module is I'm really emulating this course. Okay, I better not. Okay, so last session, we were discussing the Michaelis-Menten equation. And again, I want you to remember this equation. We said the rate of a reaction equals Vmax, sorry, Daria, times the substrate concentration divided by Km plus the substrate concentration. And we looked at the different ways or the different things, what they are telling us. So again, this was here the rate. This obviously is the substrate concentration. So substrate concentration. Indeed, a deep sigh. Vmax is the maximum speed of the enzyme. And that happens, or maximum rate. This happens when all the active sites of the enzyme are occupied. And Km is the substrate concentration. That results in half of Vmax. So these were the three, that was the Michaelis-Menten equation. We said Vmax tells us how the enzyme behaves, if the substrate concentration is incredibly high, and I indicate it like that. Actually, we will get Vmax only when the substrate concentration is infinite. But we still can work with Vmax. We also said that Vmax is the total enzyme concentration times one of these rate constants, this K cat, the catalytic constant, and that is one of the rate constants. And we will need this equation later on. So that is what Vmax tells us. Incredibly high means very high. We also said on Wednesday, we have another parameter, Vmax over Km. And this tells us how the enzyme behaves if the substrate concentration is incredibly low, almost zero. And again, Vmax over Km depends on the enzyme concentration. So Vmax over Km depends on the enzyme concentration because Vmax depends on the enzyme concentration. I can write this here as well as E depends on the enzyme concentration, like that. So Vmax, very high substrate, Vmax over Km, very low substrate concentration, and both depend on the enzyme concentration. Km tells us, as I just said, the substrate concentration that gives half of Vmax. And it tells us about the affinity of the enzyme for the substrate. For substrate. Km high means we need lots of substrate. Let me just move this thing here. We need lots of substrate. So Km high, this means low affinity. And likewise, Km low, this means high affinity. We need only diddly squats. We only need diddly squats of substrate in order to get half of Vmax. That is when we have a low Km. So low Km, high affinity. And Km does not depend on the enzyme concentration. Okay, that is, I think, where we stopped yesterday. Right. I also showed you how we actually can plot these data. And here we have the substrate concentration. And here we have the starting rate, the initial rate, the speed of the reaction. And I showed you this graph on Wednesday. And what I have done is I have done another graph here where I have just simply, this one here, doubled the enzyme concentration. So this one here is 2 times the enzyme concentration. 2 times the enzyme concentration of the first one, of the first initial rate. And here are actually the two graphs. So the blue one is with 1 times enzyme, and the red one is with 2 times enzyme. Now here on the x-axis we have the substrate concentration, on the y-axis we have the rate. What would you think for the blue graph, what would you think Vmax is? What is the maximum velocity for the blue graph? What rate? The maximum velocity, the rate for the blue one. Yeah, I think 100 is not a bad value. It's not a bad value. It looks like this is our last data point, close to 89, and we know that Vmax must be larger than that. So I think probably 100 would be a good, probably around 100. What's the unit? Millimolar per minute. So that looks reasonable because if we look at this 100 here, this is where this graph probably ends up if we have the substrate concentration almost infinite. It wouldn't reach 100 if it was exactly 100, the Vmax. The graph would not reach 100, but it would get close to it. So can we find out what the Vmax for this one is, for the blue graph? Well, all we need to do is we need to take for, what did I say? Vmax? No. Can we find out what Km for the blue one is? Km is, how do we find that? Well, we know that Vmax, or we say Vmax is about 100. So half of Vmax, therefore, is 50, right? So all I need to do is look at the graph and say, right, here is 50. So what is the substrate concentration? That gives me 50. And we find here 50, this point here would be our Km. So that's about 25 millimolar. You see what I've done? I said Vmax is 100. I need half of Vmax. That's 50. And now I find the substrate concentration here. That gives me this 50 rate. Make sense? Are you happy with that? Great. Okay, now let's just quickly move this. And let's have a look at the red graph. Okay, that's the red graph with two times the enzyme concentration. What would we say would be a Go back. What would you say is a reasonable Vmax for the red graph, if you look at that? $175. It can't be 175 because we know that it must be larger than the last point. Let's say 200. And the unit for a rate in this case is always concentration over time. So it would be millimolar per minute. So can we find Km for the red graph? Km? How do we find Km? Let's go for 200 as an estimate. So what we find is half of Vmax, and that would of course be half of 200, that's 100. So 100 here. And in order to find the substrate concentration that gives us half Vmax, we just go over to the red line and then go down and try to figure out what our Km is. Oh, look at that. What is Km in this case? Again, Km is 25, and it has the same unit as the substrate, so Km is 25 millimolar. So I changed Vmax by adding more enzyme, but what you see is that Km is totally not affected. I can change the enzyme concentration, but Km will not change. And that is something that a lot of people find really weird. But this is what we've stated here. Km is not affected by the enzyme concentration. It's always the case. And Vmax, we just simply estimated from our curves here. We said 200 is probably where this line, where this red line will go if we add more and more substrate. Okay, happy with that? So Km is not affected by the enzyme concentration. And indeed, the Km tells us about the affinity. So the enzyme shows half maximum speed when we reach Km, when we have Km. The enzyme, the affinity, it is basically, how shall I say, it tells you how much the enzyme likes the substrate. But this, how much I like chocolate, does not depend on how much chocolate is there. It just tells people how much I like chocolate. So Km is independent of the enzyme concentration. It just tells us how much the enzyme likes the substrate. Now, we can have a little bit of fun with the Michaelis-Menten equation. And we can say, let's assume we have a rate V is 50% of Vmax. No, yeah, absolutely. Km can be any number. This was just an example. And it depends on Vmax, obviously. So let's say the rate is 50% of Vmax. What is the substrate concentration? What substrate concentration gives us this rate? And actually, that's a question that will come up in the multiple choice test next week. That's one of the questions that I've said, where you have to calculate what substrate concentration gives a particular rate. I shouldn't have said that, but I did. So, you know, and there are practice questions on the enzyme. On the enzyme practice calculation website. You just work backwards, exactly. So let's say, here's our Michaelis-Menten equation. V equals Vmax times S over Km plus S. Right? Yes, indeed. And what we know is that if we bring this Vmax to that side, we have V over Vmax equals substrate concentration over Km plus the substrate concentration. All I've done is put the Vmax down. And I know that V over Vmax, that is just simply 50%. That is my 50% that I had up there. So that would be 0.5 equals S over Km plus S. Right, now let's find S. All we need to do is rearrange this equation a little bit. So I multiply both sides by Km plus S. What do I get? I get 0.5 Km plus S equals S times Km plus S divided by Km plus S. Are you happy with that? The 0.5 is from the 50%. That's absolutely right. Have I made a mistake anywhere? I hope not. Okay, so the Km plus S cancels out. That makes it easy. And we have 0.5 Km plus S equals S. Why do you think Km is squared? These are just lines to indicate what I'm doing here. Good point. I just want to illustrate the general principle, because the next thing that you have to do is apply this principle, how you rearrange the equation, and do it for yourself. So what we get here, we multiply this in here, we get 0.5 Km plus 0.5 S equals S. So what I do next is I bring this one here to the other side. I have 0.5 Km equals S minus 0.5 S. And if I do that, what is S minus 0.5 S? What is S minus 0.5 times S? Exactly, 0.5 S. So I have 0.5 Km equals 0.5 S, or I can say 0.5 times not this one in the brackets, 0.5 times S equals 0.5 Km. So what is S? Well, just divide both sides by 0.5 and I get S equals 0.5 over 0.5 Km, or my S is 1 times Km. And that is not surprising at all. This is not surprising at all, because we know that at Km is the substrate concentration That gives us 1/2 or 50% of Vmax. So that's exactly what we said originally. But what I wanted to show you is the way you need to calculate that. Because sometimes it might not be 50%. For example, let's do a nice little other example for that. Are you ready? Probably not. Go away. Right. Let's say we have V equals 20% of Vmax. What is the substrate concentration that gives us these 20%? What is the substrate concentration that gives us 20%? And we want to express it in multiples of Km. What is the substrate concentration? I give you a couple of minutes to try it yourself. So 20% of Vmax, what is S? And here's basically what you need to do. Oh, yes, it does. So what is the substrate concentration that gives us 20% of Vmax? Juby, I think you are on a winner here. Shall we quickly do it together? So that people are all right with that? Shimek, yeah? Okay, so what we have is V over Vmax. That is 20%. We know that. And that is 0.2. 0.2 equals substrate concentration divided by Km plus the substrate concentration. So all I need to do is bring that to the other side, and I have 0.2 times Km plus the substrate concentration equals the substrate concentration. Absolutely right. So we multiply that in, and we get 0.2 Km plus 0.2 S equals S. Right? I bring that to the other side, and I have 0.2 times Km equals 1 minus 0.2, so that would be 0.8 S. So I've got 0.8 times S equals 0.2 km. I divide it by 0.8 and I get an S equals 0.2 divided by 0.8 times km. And if I do that with a calculator, I get 0.25 times km. So at a substrate concentration at 0.25, a quarter of km, I get 20% of Vmax if the enzyme follows Michaelis-Menten behavior. The 0.8 comes from S minus 0.2S. Because I put this 0.2 to the other side. Okay? One minus 0.2, and that gives us this 0.8S. Absolutely right. But usually we are not terribly interested in what substrate concentration gives us a Vmax or something like that. Very often we are more interested in what is the Km. We can do the analogous procedure. Let's say we have, what have we got? Let's say we have, let me think about it. Oh yes, let's say we have a substrate concentration. Our substrate concentration is 50 micromolar, right? And at 50 micromolar, we observe our rate, which is 30% of Vmax. What is Km? How are we going to do that? Well, let's think about it. Okay, we've got our Michaelis-Menten, V equals Vmax times S divided by Km plus S. And what we are looking for now is Km. Well, you know, we just have to do a little bit of rearrangement. So we bring that again down here, as we've done before, because that's 30% of Vmax. V over Vmax equals 30%, and that is 0.3. And we know that this is equal to S over Km plus S. Okay, so what we do is we bring that again to that side, and we have 0.3 Km plus S equals S, right? And again, I multiply that in, and I get 0.3 Km plus 0.3 S equals S. I'll bring that to the other side. And I have 0.3 Km equals, what do I have on the other side? What do I need to write on the other side? It is 1s minus 0.3s, and that gives me 0.7 times s. Absolutely right. So I have 0.3 km equals 0.7 times s. I bring that to the other side, and I have km equals 0.7 over 0.3 times s. And I know, I told you, that we have an S of 50 micromolar. So what we can do in this case is we can just simply plug that in, equals 0.7 over 0.3 times 50 micromolar. So what we get then, if we put that into a calculator, what do we get for Km? Km in this case is, what do you get if you put that in? Yep, 116.7 micromolar. That's absolutely right. So that means if we have an S of 50 micromolar and we get 30% of Vmax, then our calculation says Km equals 116.7 micromolar. Easy. Because we know that V equals, let's say, 30% Vmax, or we can say equals 0.3 times Vmax. So if we've got 0.3 times Vmax equals Vmax times S over Km plus S, what you see is that the Vmax cancels out. Does that make sense? So that's how you do these calculations. We have one more type of calculation that we need to deal with, but that's really easy, this one. What is this doing here? Why is it calculate? Why is it cutting out? I would just simply go for the unit that S is given in. So if you actually have an S given, then like you had in this case, then you can easily do the right unit. If you don't have an S given, like we had in this previous example, then you can express things as multiples of Km, for example. Now we have one more calculation to cover, and that is I told you, oh, what's the matter with this thing today? Vmax. And I know, Daria, that's the one thing that you absolutely hate. Vmax depends on the enzyme concentration. We said that, didn't we? And the equation for that is Vmax equals the total enzyme concentration times K cat. That's one of these rate constants. Oh, thank you. Are we back in business? Screen should be up. Okay, so the screen is back. Cool. Sorry about that. I think my iPad had a bit of a blonde moment. So Vmax depends on the enzyme concentration, and Kcat, that is one of these rate constants, and that's a very special rate constant for the reaction. So let's say we have a Vmax, let's say, of 100 micromolar per minute. And let's say our total enzyme concentration, let's say we have 100 picomolar. And I told you enzyme concentrations are really, really small. They're much smaller than usually the substrate concentration. So can we calculate our rate constant, this Kcat? And obviously we can. So Kcat, this rate constant, equals, well, all we need to do is do a little bit of rearranging. Vmax divided by the total enzyme concentration. Yeah? Are you happy with that? So all we need to do is we need to plug in our numbers, but we need to be aware that we have different units. So we convert that all to the same unit. So we have 100 times, what is micro? 10 to the minus, thank you, 100 times 10 to the minus 6 molar per minute. And we divide that by the total enzyme concentration. So we have 100 times 10 to the minus, what is pico? $12, thank you very much. Molar. So what happens? The molar cancels out, the 100 cancels out. And we've got 10 to the minus 6, 10 to the minus 6 divided by 10 to the minus 12. And we've got the minute down here in the denominator. What is 10 to the minus 6 divided by 10 to the minus 12? 10 to the minus 6 divided by 10 to the minus 12. It is indeed 10 to the power of 6, or 1 million. And the unit is per minute. So we have kcat in this case. Kcat is 1 million per minute. Okay, 1 million per minute. Usually the unit for kcat is expressed in per second. So all we need to do is we divide 1 million, 1 times 10 to the 6 divided by 60, then we get it in seconds. And we get something like 16,700 per second. I just simply divide the value per minute divided by 60, because I've got 60 seconds in 1 minute. So that is 16,700 per second. What on earth does this number tell us? This number tells us that the enzyme, well, let me phrase it this way. One enzyme molecule converts 16,700 substrate molecules into a product every second. This is what this number tells us. And as Tay says, this is a lot. One enzyme molecule converts 16,000 substrate molecules per second. Are you impressed? This is absolutely amazing, isn't it? And that shows how powerful enzymes are. But that is not the best. I've got a little table here. Here is, for example, an enzyme where you see probably catalase. It has a kcat of 40,000 of 40 million of 40 million substrate molecules per second. 40 million. This kcat, actually, it tells us how fast the enzyme turns around the substrate, and therefore kcat is also known as the turnover number. Absolutely right. That's absolutely correct. That's the explanation why this enzyme, this catalase enzyme, is so incredibly efficient. So kcat tells us how fast the enzyme uses the substrate, and there are some absolutely impressive numbers in there. Our enzyme with 16,700 per second is sort of bog standard. It's nothing really totally exciting to write home about, but these turnover numbers can go into the million and 10 millions per second. And that's an absolutely amazing thing. So what I want you to do is I have set up some calculations, practice calculations on my enzyme website, or on the practice calculation website. And I would strongly recommend to you that you go through these calculations that I showed you today, because it might be worth looking at them for the MCQ test next week. Okay, so, well, I hope you have a lovely weekend, and thank you very much for watching, and well, enjoy practicing. I have no idea when the test is. I think it is on Friday. Have a lovely weekend, and I shall see you next week. Take care, be good, don't do anything I wouldn't do.
Goodbye.
Bye.